Hello, welcome to the NPTEL course Fundamentals of Composite and Cellular Materials. The topic for today's lecture is cellular solids, applications of porous ceramics and polymer foams. In the last lecture, we covered the topics cellular solids, applications of metal foams. Then in applications of metal foams, we discussed about the structural applications, functional applications and architectural applications. It was shown that metal foams are used in multi-form from applications like starting from structural applications like in automobiles, aircrafts, then in railway applications to many functional applications like also for thermal applications and also for acoustic applications. The main topics that will be discussed in this lecture include the applications of porous ceramics. There we will be discussing about many functional applications, then applications of porous ceramics for metal ceramic composite fabrication. So, this is one very big aspect where ceramic foams are these days used, and then we will discuss about the applications of many polymer foams. The keywords to be covered in today's lecture are porous ceramics, their application as ion exchanger, catalyst carriers, bioscaffolds and interpenetrating metal ceramic composites, and then for polymer foams we will discuss about the thermal and sound insulation, electromagnetic shielding and so on. So, let us start with the applications of porous ceramics. So, the left hand side image actually shows the benefits of porous ceramics and their manifold properties. So, as we know, ceramics have properties like high strength, high Young's modulus, then they also have good properties like hardness, wear resistance and so on. Ceramics are also very good for high temperature applications because of their high melting point, and they are also resistant to corrosion. At the same time, porous ceramics they actually offer properties like very high surface area, and if a porous ceramic this high porosity is combined with the good properties of ceramics, we get excellent properties like excellent wear resistance, low thermal conductivity. This is because ceramics as such have low conductivity, and because of the presence of a high amount of porosity, the porous ceramics have very good insulating properties. Porous ceramics also have good corrosion resistance. They provide excellent surface area. As I already mentioned, because of the large porosity, porous ceramics have high surface area, and this surface area can also be adjusted by adjusting the amount of porosity and the pore morphology. As such, as I already mentioned, porous ceramics have very high temperature resistance. There are some ceramics like zirconium diboride or other borides and carbides which have even melting point more than 3000 degrees Celsius, and these porous ceramics can be very optimum for applications for very high temperature applications like exhaust gas applications and so on. Porous ceramics also provide high hardness because ceramics as such have high hardness. Porous ceramics also have very low density. As we discussed in a previous lecture, ceramics as such have low density because of the presence of non-metallic elements like carbon, oxygen, nitrogen and so on, and because of the very high amount of porosity in the porous ceramics, the porous ceramics have very low density. They have great strength, but again we have to remember that when we use ceramics or porous ceramics, the strength means it is either the compressive strength or the flexural strength. Porous ceramics or as such ceramics are very poor when they are applied into tensile loading, and because of their controlled porosity, the porous ceramics can also have controlled permeability, which is again good for fluid transport applications like afterwards we will see for applications for ion exchanger or also for filtration applications, where porous ceramics can actually provide very high amount of permeability. In the next lectures, we will discuss about the fabrication processes for porous ceramics, But what we can see from the right hand side table or this image is that porous ceramics can actually be fabricated over a high amount of porosity, starting from almost dense ceramics to a very large amount of porosity approaching more than 90%, and the pore size can also be varied over a wide range starting from nanometer range to even millimeter range. And there are different applications or fabrication processes which actually control this both porosity and the pore morphology and the pore size. But what we can see is that for many applications the porosity actually varies in the range, in the mid range, from up to 30% to 70%. Like we can see the applications like hot gas filter, then diesel particulate filter, water filter, catalyst support, all these applications actually require porosities in the mid range of 30 to 70%. And also the pore size also varies. Typically the pore size, although there are applications of this microporous ceramics with less than few nanometer, but typically the pore size of porous ceramics for structural applications and for the applications which will be discussed in this course, they typically lie in the micrometer range, like starting from a few micron, like maybe 1 micron to up to 10 micron to 100 micron. This is typical pore size mostly used for the applications which will be discussed in this course. Now, after this basic introduction about the main properties and structure of the porous ceramics, we will discuss about some specific applications of porous ceramics in this lecture, and in one of the future lectures, maybe next 2-3 lectures, we will discuss in detail about the various fabrication processes used for porous ceramics fabrication. So, starting with the main or some applications of porous ceramics, first we discussed about the porous ceramics as ion exchanger. So, as we know that there are that many a times the water that we drink or used for many applications, these are actually kind of combined with many highly toxic and heavy metals like arsenic, antimony, cadmium, mercury, chromium, magnesium, etc. And these heavy metals, the presence of these heavy metals in the water can actually be very detrimental for our health, because they can actually give rise to long term physiological problems and also cause diseases like cancer in the long term. As we know that arsenic or lead, for example, cadmium for example, these are extremely dangerous materials if they actually accumulate inside our body. Also these heavy metals actually make the life of the containers where the waters are kept, water is kept, they reduce the life of the containers, because they can actually form layers on the container surface, and this way the container lifetime can be reduced significantly. Now, porous ceramics are actually very attractive material for ion exchanger applications. For porous ceramics, they actually provide, as I already mentioned, because of the very large amount of porosity, and if this porosity is interconnecting like open porosity, then actually we provide a very high surface area for the water to pass through. And then this ion exchanger may consist of a continuous, because the porous ceramics provides a continuous skeleton, and then with fixed co-ions, the harmful ions like these harmful elements or metal ions can actually be exchanged for the desirable ion, and in this way, with maintaining the same amount of polarity, the ion exchange takes place, and this way the harmful ions are removed from the water before they are actually supplied for further applications. And this diagram actually shows the basic application, the basic principle of how the ion exchanges actually work. And these porous bodies, what you can see over here, these are actually the porous scaffolds, and as we know that the porosity and the pore morphology can actually be varied over a wide range to actually facilitate the proper ion exchange process. After this, next application where porous ceramics are very useful are for catalyst carrier. Again this catalyst carrier, again they are like for many applications like containing gaseous pollutants, or like and in these cases like they also have pollutants like the heavy metals and other contaminants in water or wastewater treatment. And again for these applications, porous ceramics with a very high amount of porosity and pore morphology and interpenetrating porosity can actually provide a very good material for catalyst carrier. And also porous ceramics many applications or many properties like the very good corrosion resistance, high temperature stability, high permeability, low density, etc. They actually provide very good option for both catalyst support for both gas and liquid phases. And again typical working principle for this porous ceramics for catalyst carrier is also shown in this particular slide over here. And as you can see that as the contaminants, as a medium containing contaminants is actually passing through the porous ceramic body with the catalytic membrane, they are absorbed, and this way a pollutant free porous ceramic this water or other medium can actually be obtained. Porous ceramics are also excellent for filtration and separation purposes. Now, filtration is again very useful for many applications, typically for metal fabrication in metal casting, because as we know that non-metallic inclusions like oxides and all those things can actually affect the properties of the metals like the strength, machinability and toughness. So, in those applications to remove those non-metallic inclusions, the liquid metal can actually be passed through a ceramic foam filter. These are typically called ceramic foam filters, and again there are properties like the high porosity, the high temperature resistance of the porous ceramics, and also there are other properties like the corrosion resistance can actually play a very good role over here. And as those molten metal is actually passed through the ceramic foam filters, then those non-oxide or oxide contaminants or those inclusions can actually be trapped by the ceramic foam filter, and we can obtain a clean metal. Now, many such ceramic foam filters have actually been developed, like as you can see over here there are foam filters typically of silicon carbide, and these are actually fabricated by replica method, which have even millimeter size porosity, and the pores are interconnecting, and this porosity can actually be defined. Many a times these large pores, they are defined, not defined in micron scale. They are typically, one term is used called PPI or pores per inch, and there is a very wide range of porosity like from 10 PPI or 30 PPI. These pores can be, or these porous bodies which are with a very wide range of porosity and the pore size can easily be fabricated by many methods. Typically replica methods are used, which will be discussed in a future lecture. But what is more important here is that these porous bodies with a very wide range of porosity and pore morphology are excellent materials for filter applications for metal casting applications. Also, porous ceramics find wide range of applications as bioscaffolds. So, scaffolds are typically used for support materials for bone structure, and these scaffolds should have many attractive properties, like they should have interconnecting open porosity through which the new tissues can grow, and also they must provide a path for avenue for nutrients and all those things. And for these porous ceramics, because of their biocompatibility, they can also be excellent materials for scaffold applications. Like there are many scaffold materials have been developed, like hydroxyapatite or bioglass scaffolds have been developed, and also there are materials for prosthetic applications like for ZTA, like zirconia toughened alumina or alumina toughened zirconia. So, these materials are very useful for biological applications, and for these bioscaffold applications again porous ceramics are very appropriate because of their high range of high corrosion resistance, and also the porosity can be varied over a wide range. So, typical scaffold applications are also shown over here. So, as you can see this again the morphology of the porous ceramics can actually be varied over a wide range to actually mimic the properties and the structure of the bone where the scaffolds will be used. And here there are many applications where these have been used, like there are silicon nitride, then hydroxyapatite. These have often been used for such kind of application. Then one very this is a new application, but nowadays these are being used more and more. these porous ceramics as preforms for ceramic metal composites. So, as we know that normally the ceramic metals, I mean the ceramic materials, if it is a bulk ceramic, they have very low fracture toughness, typically less than 5 megapascal root meter, and typically for structural applications we need a minimum value of around 15 to 20 megapascal root meter. So, typically these ceramic materials, whenever the bulk ceramics are used for structural applications, their application is very much limited, because they cannot be used for many structural applications. So, they are actually a composite material where a combination of a ceramic and metal can be used, and in this way typically this metal matrix composites, where a metal containing a small amount of particles, ceramic particles like many ceramics like alumina, silicon carbide, silicon nitride, these actually have been used very often for many applications in automobile, in aerospace and all such cases. But when these metal matrix composites are used with kind of individual ceramic particles, the particle content is very much limited, like up to around 10 volume percent or something like that, because if it goes to more than that, then fabrication becomes pretty difficult. Powder metallurgy process can be used, but again powder metallurgy process has the limitation of a small a small component size, and for that cases actually a new class of metal ceramic composites which are called interpenetrating composites have been developed. So, where what is used, first a porous ceramic is fabricated by whatever process. The porous ceramic should have a high amount of open porosity, because that will actually provide the interconnectivity, and then this porous ceramic can actually be infiltrated with a metal, typically light metals like aluminum, magnesium can be used, and the porous ceramic can be made out of any ceramic, like typical applications have been prepared with alumina ceramic, silicon carbide, silicon nitride and so on. And then this porous ceramic, because it has, after fabrication it should have sufficient strength for handleability, and after sintering it has porosity over a wide range, like in the technically important range of 30 to 70% porosity can easily be fabricated. And then these porous ceramics actually infiltrated with the liquid metal under pressure by squeeze casting and or gas pressure infiltration, and this way these interconnecting pores are fully infiltrated and one obtains a metal ceramic composite with a very nice interpenetrating structure. So, typical schematic of such a composite is shown on the left hand side. So, as you can see, these both phases actually here are interpenetrating, and here actually there is no matrix, because normally in a composite actually the matrix was used for the continuous phase, and inside the matrix the reinforcement phase is distributed in a homogeneous manner. But in such a IPC or interpenetrating phase composite, both the ceramic and the metal, they actually form kind of co-continuous network, and here both phases actually are interpenetrating. So, some examples are shown on the micrographs. As you can see over here, this is a typical IPC fabricated by, first alumina foams were made, and then within the alumina foams the aluminum metal were actually infiltrated, and as you can see over here, these alumina foams are actually shown by these black portions in the optical micrographs. They actually show the alumina foam, and then these white regions are actually the metal. So, you can see it is a very nice co-continuous structure with a very less amount of some porosities are there, but the pores are very less in nature, less in content, and this is a very good structural material. And you can see, if we see the properties of this porous material, we can see over here that, so this is again plotting of these IPC materials in the typical HB plots, like the specific modulus over specific strength, and also thermal conductivity over thermal expansion coefficient. And as you can see over here, these interpenetrating phase composites with both metal and ceramic interpenetrating or kind of co-continuous, they actually provide very nice properties, like they are even better than the particle reinforced composites typically used for metal matrix composites. Like in the left hand side plot, you can see that these porous that these composites actually have higher specific strength and higher specific modulus over the particle reinforced composites, and on the right hand plot you can see that these, because these porous ceramics, because they have a very as such ceramics have low expansion coefficient, and now this co-continuous nature will actually provide even more resistance to expansion of the metal when it is heated. So, that is why reason you can see that these materials for similar amount of conductivity, like the conductivity is more or less similar, but they actually provide much lower expansion coefficient. So, these materials are very good for thermal shock resistance, because for thermal shock resistance, as we already discussed, the material should have low expansion coefficient and high conductivity, and because of its co-continuous nature, these porous ceramic bodies when infiltrated with the liquid metal, they actually provide very good thermal shock resistance. So, these were some applications or application domains where these porous ceramics can be used, and next we will discuss about some application domains of polymer foams. So, polymer foams, again as you can see in this schematic over here, they again have many nice properties, like they have like biocompatibility, they have low density. So, polymer foams, one of the main applications of polymer foams is there for structural application is the low density, because as you know that these polymers, they typically have a low density than the metals and even ceramics, and because we introduce high amount of porosity in the polymer foams, these polymer foams have even lower density, and that is the reason that these polymer foams are very good materials for structural applications where high specific strength and specific stiffness are required, and some applications will be shown afterward. But apart from that, these polymer foams are also very nice materials for biological applications, also for EMI shielding applications, for thermal applications as insulation and all those things. So, these will be briefly discussed in the next few slides. So, first we discussed about the high performance applications in lightweight applications. So, like as we discussed, the polymer foams, they have a very high amount of porosity, and because the low density of both the foam material and because of the high amount of porosity, the density of the polymer foams are even lower, and then these polymer foams can actually be fabricated with having density, having the specific properties like stiffness over strength over stiffness over density or strength over density even better than the metallic materials, and these actually make these polymer foams very applicable for many applications where density is a very critical factor, like applications in automobile applications or aerospace applications. Like as you can see over here, that many parts of automobiles or modern automobiles are actually fabricated by polymer foams, like also for those applications where crash is an important factor, like these polymer foams can actually deform over, and these can actually be giving protection to the inhabitants, like similar to metal foams, and also for aerospace applications like for those sitting appliances and all those applications, polymer foams are actually very attractive materials. Also for applications for thermal and sound insulation. So, as we already mentioned, for energy efficiency, one needs to maintain the thermal insulation, and for those applications like polymer foams, they typically have low conductivity, and also for the presence of high amount of air in the polymer foam, they actually are very nice materials for those thermal insulating properties. Also polymer foams have many other attractive properties, like their good mechanical properties and also their flexible nature, and because of that, for many thermal applications, polymer foams are very attractive materials. Also, as we discussed for the metal foams in the previous lecture, these open cell polymer foams can also be very nice materials for sound absorption, because as we know that for sound absorption, the open cell nature is very important, because again the interpenetrating nature of the foam is very important, because otherwise the sound will be only reflected. But for sound absorption, it is important that how the propagating sound wave actually is kind of interacting with the cell walls and the cell faces. So, as you can see over here, as the sound wave is actually propagating through the material, as is being shown in the image C, that because of the intermittent reflection and transmission, so the sound intensity is actually reduced significantly, and because of that, these polymer foams are very nice materials for sound insulation applications. Also for EMI shielding, like this with more and more use of wireless communications, this electromagnetic pollution is a very important factor, and again these polymer foams, they can be used because of their lightweight, easy processing, chemical resistance, and also good mechanical properties and eco-friendliness. And there actually this conducting polymer foam composites or like CPCs, where actually their polymer foams are actually reinforced with some nanofillers like graphenes or CNTs or carbon black, metal particles, etc. And again these actually are very nice materials for because of their tailor-made conductivity and dielectric properties. So some examples are again shown over here. Again the mechanism is being shown over here. This polymer foam, this open cell polymer foam, again here again the open cell nature is very important, and again one can see that as these incident EM waves are kind of how they are actually absorbed and how they are reflected, and this way they can actually control the electromagnetic shielding applications. Polymer foams are also used for tissue engineering, just like for scaffold fabrication, again the open porous nature, and also for this high surface area, and also for the non-corrosive nature. They can again be used, and many methods can actually be developed, like particle leaching, solvent casting, 3D printing. So all those methods can actually be used for fabricating these open cell polymer foams for many tissue engineering applications, as is being shown over here. So here for example one method is being shown over here. So how this open porous polymer foam is developed, and how this can be, like this can again be the pore structure, and the pore morphology can actually be tailor made to actually mimic the structure inside the body for which this polymer foam will be actually used. So again we have in this lecture we have shown many applications of both porous ceramics and polymer foams. So we have seen that porous ceramics are used for many applications because of their many attractive properties, like high melting point, which gives the high temperature resistance, then their good strength and stiffness, and also for their high hardness, which actually provides the high wear resistance, and the combination with the high amount of porosity, which actually provides a good surface area. These porous ceramics are very attractive materials for ion exchanger, catalyst carrier, filtration and separation, bioscaffolds and so on. And porous ceramics can also be used for a sacrificial material to actually develop these ceramic metal composites, where the porous ceramics are infiltrated with the molten metal, and these IPCs or the interpenetrating composites can actually have very nice properties like high specific strength and stiffness, and also excellent thermal properties like low thermal expansion coefficient, and they are very nice for those applications where thermal shock are very important. Also some applications of polymer foams were shown, like these polymer foams, again metal foams and porous ceramics. These polymer foams also have a very high amount of porosity, and polymers inherently have a low density, and when combined with the low density with the high porosity, these polymer foams have even lower density, and then this can actually be tailor made for many applications, like for structural applications in automobile and aerospace, and also for other applications as thermal insulation, sound insulation, and also for electromagnetic shielding, and also for many biomedical applications. So in the these are the references which were used for this lecture, and in the next lecture we will discuss about the fabrication of cellular ceramics, and there some basic processes like how the powder consolidation is made, and how the various initial processes like die compaction and how they actually affect the final ceramic foam structure will be discussed in the next lecture. Thank you very much.